Alrighty. Welcome back, friends. Hope you are well and holding together in these times. I'm Agent Ultra, and we're gonna chill for a little bit and hang out. I program stuff in the language Haskell on this stream, and I build practical things, hopefully. Sometimes not always practical. Lately, we've been learning how to implement wave function collapse. And we kind of maybe got it working. The algorithm, at least. And we've been working on the visualizer for it. So kind of building a front end in SDL to try out the library, tie things together, see it generate some textures for us. Because if you don't know, wave function collapse is a procedural generation algorithm, which is a fancy nom de plume for algorithms which take tiny thing and make bigger thing. In this case, we take a tiny input texture, and then the bigger thing we get is an output texture that has a lot of self-similar properties to the input one. So it's not entirely random. There is like a methodology to it that makes it look the way it does, and it's used a lot in like game development and just for like creative coding and stuff like that. And yeah. I'm just learning it because it's sort of a interesting kind of algorithm, I guess. I don't know. It seemed fun and like a good idea, so why not, right? Also, like, just getting a handle on implementing some bigger algorithms in Haskell. And stuff like that. So let's look at the code. And let's get going. I'm going to open... I think I got some stuff in my to-do file that we can work on here today. Visualizer. Yeah, we have the loading texture stuff done. We're in the middle of get texture. And then render it. So getting the texture here is... Well, this is something we might have to fix or address somehow, but... Texture here, there's two different kinds. There's the SDL texture from the graphics library, and then there's the data structure we use as the input format to the library. So we're not working with textures directly in the library. It's kind of parameterized over the data because we just need some structure. We don't really care about the pixel data itself, just that we have some of the values there. We don't really inspect the pixel values themselves. So that's all abstracted over in the library, and that data structure I call textured. Yeah, in retrospect, not the best idea, maybe, but it seemed fitting at the time. So the get texture stuff is basically getting things out of the algorithm once it's done running. We want to create a texture from that, and then users can take that texture and convert it to the texture format of their library that they're using. In this case, we're using SDL, so we'll get a heads up on what that's going to look like for our SDL users. Cool. So without further ado, let's go into... So we're going to be doing a lot of work in the library at the moment. This is the app code, this is the front end code. So let's go over into the library. Algorithm, wave function collapse, boom, in here. Okay, so we have a bunch of undefines in here that we need to define this week, and that's what we're going to do. That's what we're going to get started with. Okay. Possibly addressing this to-do here as well, because that's going to be a thing. All right, hydration. Skadoosh. Much better. Okay, chat. Let's make sure I got you pulled up here. Cool. All right, so we got to get the collapsed pattern index. We get a grid cell, and we need to get either an error string or a pattern index out. All right, and that is used. Collapsed pattern index. Ah, yes. Okay, pattern indices. So we get the grid, we get the cells out of the grid, and then we're traversing over that, getting all of the pattern indices out of the collapsed pattern. So this function should return left if the cell is not collapsed. Shouldn't happen at this point, but we're forced to handle it. And yeah, so that's the first thing we can do. So if the grid cell is a cell that is, it's not collapsed, or sorry, left, it's kind of our first case we need to handle. And then the other case is that we have a collapsed cell. That's good. And then we have the pattern index from it. So we could just return that. And then in this case, we know that it's a problem. So we can put output texture. We don't know the cell index of this cell at this point in time. Okay, it's probably gonna bite us, maybe, potentially, later. Maybe at the grid location? Okay. That's the basic version of it. Okay, get pattern. Right, and so we get the pattern results. So that's when that's from data from an earlier stage in the algorithm where we get the set of patterns that we're going to be using to generate our output grid. So the output grid only has the pattern indices, the indices into our pattern result set. So we're going to get those patterns out now with this function. Our pattern result A, pattern index. Okay, so the pattern result, that has some data in it. It's got the list of patterns. So the index goes into this here. I lost my spot. I forgot to... There we go. Okay, get pattern. So, pattern results and the pattern index. Okay, we can guard this a little bit because we know the max index in pattern result. We saw that there. So, in that case, when the pattern index is less than 0, or the pattern index is greater than the pattern result max pattern index, we'll get the error that well, you can't do that, bro. Do that, friend. Not allowed. We'll say that get pattern index out of range of collapsed cell. And we got a type error there. Oh. And that's because we want to use this name, probably. Okay. Then, otherwise, what else? Otherwise, we're fine. We can go in here. We've validated our parameters. Then we need to case match on the index into the list. We'll do that with pattern index into list dot, I think it's bang bang, on pattern results, patterns of, that should be an equal sign. If we didn't find anything, or if we found it. We actually want that pattern. I can't call that the keyword. We'll just call it pat. And we'll just return pattern. Otherwise something here. I think I just got I'm on the wrong side. Is this music on repeat? Sorry, folks. Let me skip that here. Okay, and what do we got here? Oh, bang bang doesn't do, or maybe. Oh, okay. Oh, what is it? It's got to be like find or something like that. Look up. Association map. No, find. Indexing. Right. This one's the partial one. I would prefer the safer one. I don't usually index into lists, so I have to look it up. That was me. Alright. Element index. That's switching for an element that is equal. That's not what we want. That's not what we want. No, no, we will. We could write a helper function to do a safe version of this. It might bite me in the butt saying this, but we could also just use that indexing thing and not worry about it, because technically all these indices aren't coming necessarily from the user, so it should all be in bounds. And if they're not, then we're gonna get our program's basically gonna blow up, as we've seen happen when using arrays and indexing things inappropriately. This Shadows? Okay. Okay, I guess I'll just rename it to E results. Praising people. Alright, P result it is. Sorry, chat, if that's a weird name to pick for a variable. Okay, hydration. It's getting dry in here. The winter weather is starting to sink in. The harness is on. It makes my house dry. Alright, get pattern pixel now. This is where this is the function where we just have to get the top left pixel of the pattern. So the one at 0, 0 in the pattern's texture. Which is defined up here. Get the pattern size, and then you get an array. We just need the one at 0, 0, the top left, which is just that by convention. Actually, let me get pattern. Okay. From that, we need an array function to index into that array with our kind of pre-picked index. And I think we can just do the same thing we did for lists as well. So we know that there's a minimum size which will include 0, 0 always in all of them. So we should be able to just bang into it. Yeah. And we want to use it as a function. The first argument to it is the array, and then the index. So we're gonna flip that and give it the index 0, 0. And let's get patterns coming from the wrong thing. Let's get that. Go back to pattern. Get pattern. That's the one we want. Pattern result. Doesn't have a similarly named field, so that shouldn't be the problem. Maybe... what am I getting wrong here? On the whole. Pattern index to either string something, pattern A1, A2. No. $498. Okay, we got the pattern, yeah. But in scope. Okay, I see, I see. Oh, get pattern. Oh, I see, okay. This local binding here in the function I called get pattern, which is also the name of the field function that accesses things. So this is shadowing that currently. We should rename that. Get pattern from. Okay, now that should be fine. Get pattern. Okay. Oh, I didn't yank it properly. Oh, okay, that's fine. We're not paying that, and then give our index 0, 0. Okay. And then we just need a 2-word bound. So this is our conversion function to convert those array indices all 2-word. Which, as noted up here, we kind of have a sucky way of doing that at the moment. Or, that is the note, 2-word bounds. We have to implement the sucky way of doing it. Even more, because actually we do the from enum check already. Fly map from enum, from enum. Right. Right. Maybe there's a way we can simplify this expression, but let's just get it right first. Or is it's 2 enum, isn't it? Yeah. Okay. Well, it works so far. Let's get the builder going. Let's use the test runner as our builder. Just to make sure that everything we haven't broken. I doubt we have, but I don't think we've written any tests for it. At least this part. Okay. Cool. Okay. So that's implemented. Make output texture. Do. Everything compiles. So what we need to do now is... make sure I'm checking actually. Just hang on a second. Checking stream stuff. For some reason my dashboard isn't updating very well. My stream preview isn't up to date. Why not? Hopefully it's all live. Things seem to be connected. Chat. Let me know if you can see everything. I'm just going to reload it here. Oh yeah, that's better. Alright. I think something. Okay, we get back to the stream. Good. Okay, so let's get back onto the front end here of our application of the visualizer and see what we need to do next. Okay, so that's the from surface stuff. That's what gets all the pixels out of our SDL texture, puts it into our wave function collapse texture, and all that stuff. So then we clear the renderer, copy the image texture to the renderer, present the renderer. From surface. Okay, we get our input texture from the main there. Okay, and then that's what we're passing into. Print the input texture there. Okay, and then image texture from surface, so we're just getting the image texture from that and rendering the image surface. Okay, so the next thing for our input texture is to run the algorithm, get our output texture, get our use our new function that we just wrote to get the output texture from the finished grid, convert that back into an SDL surface image, and then pass that in as image texture into our app loop, and it should render everything. That's quite a few steps. Let's see how far we go and get this going. So first, output texture. So we got to give it the pattern result in the wave state in order to get that after we're done running things. So currently the way it's kind of set up is that we have to like run things manually. I think we should totally write a little wrapper for all of this stuff, because a lot of this is internals that user of this, i.e. me, at the moment, is not going to want to deal with when writing our visualizer app. But right now you have to use runWave, and that forces you to put it in the wave state. So you got to construct your wave state first, give it the function to run, which is our collapse wave function. And then you get a wave state back. And then we got from that wave state, we get out the grid, make the output stuff, all that business. All of that stuff. So what I'm going to do first is actually create a little committee commit for what we have so far. Add implementation for make output texture. Okay. Right, because what I want to be able to do in main here is that right, like I'm gonna have to, in order to use the library, I'm gonna have to convert to this WFC texture type in order to pass it into the algorithm to get the algorithm kicked off. Right, if I write it into the library, all the SDL handling code to get all the texture data and load it into our WFC texture, then I'm not gonna, oh, okay, actually, so From Surface already does that. Should have checked this. I wrote this. Okay, so the texture, we already get that from Surface. Okay. Okay, so input texture is already that. That's just the input, though. So now we got to construct the wave state. Right, then we run the algorithm. And we get the grid and pattern result from wave state, from the output wave state, and then get the output texture. And then we get from the texture to SDL texture or surface. And then pass that into image texture. Pass in the wave state, the wave function, the WFC made surface. Cool. Okay. Wave state. Oh, I was again in the library. Our wave state constructor. I think we wrote one, make wave state, yeah. Okay, so we give it the dimensions of the output grid here. Int is like a randomized seed. We'll use a fixed one for now. And then our pattern result that we constructed is what we have to input there. So it looks like we have to construct we have to get the pattern result first in order to construct the wave state. Input texture. Okay. That is up here. We have a function for that. Patterns. All right, so we cut out the. So this function here is what is the beginning of the algorithm, where you take that input tiny texture and you create a bunch of sub patterns out of it. All right, so it's kind of like taking a cookie cutter and cutting in the pattern, except we're not removing a piece of the pattern. So the cookie cutter is not a great analogy. We're not removing a piece of the input pattern to create the input texture for to create the pattern. We're like kind of creating overlapping patterns. And so like maybe we're like copying or tracing out sub patterns from the input texture. Something like that. That's what this function does and constructs the pattern result from that. So that's going to be a pure function. So we can just go to that equals. So we put our input patterns, wc.patterns. We give it the input texture and the size of the pattern that we want. So let's make them. Let's keep them 3 by 3. Okay. Then we have to construct the wave state. We go here. Initial wave state. That is also a pure function. So we want our dimensions here, so let's make our output dimension 30 by 30. Hopefully that's not too big for a start. And our input seed, we'll just start with, say, like 100. Which we might use like a random generator to generate for realsies, to do this for realsies. And then pattern results. Okay. Then we need to run the algorithm. So we run wave. With collapse wave. Yeah. Have output wave state. I'll rename this to input wave state. So we run wave with our input wave state. We give our collapse wave function. And then we get a final wave state. That's our output. And that'll be after the prefix of WFC. And then we get the grid and pattern result from the output wave state. It's the output texture. Here. So we give the pattern results we created earlier. And the wave state, the final wave state. And then that becomes an either. So we case on the output WFC texture. If there was some error, it's for len error. Otherwise, we'll just call this result actually. In fact, let's not bind it at all. Let's just case match on that. Alright, that's where we have to do stuff with it. So only in that case do we care about the rest of the function. Well, in the case of left, we also want to make sure that we clean up everything. I'll get rid of that. Okay. Alright, so like this code, I'm not too worried about making this code awesome. It's just the visualizer. I just want to see it work. But like we've got destroy window here and destroy window here. In either case, if the program exit, we want that to be run. So there's probably a way we could do some bracketing there to make sure that happens. But for now, I'm just going to leave it duplicated. Okay, so we have the output WC texture in the right branch here. This is where we got to convert that to a surface again. So I'm gonna, since we already have image and scope, we can call this image prime. Maybe we can go like that, let image prime be equal to surface. Output WFC texture. That might need I/O. So we might actually not be able to log bind that. So it might actually be there like that. The idea is we do image prime there, and then we're good to go. So from surface to surface. So this is where we go from a WC texture of CU int to IO surface. If I can implement this. All right. So in order to do this, I need to be able to get SDL to create a new surface for me. That's what I need first. SDL2, Haskell. Alright, SDL video. Create me a surface. Display, rendering. Okay. Create RGB surface. So we're gonna need to know the pixel format. Well, we kind of know the pixel format. I think we know the pixel format, so we can do that. Okay, so it needs the size of the surface. We know that. It's a V2. Okay, that's gonna be fine. All right, and then we get a new surface, and once we have the surface, we're gonna have to be able to update its pixel state. Obtain the pointer to the underlying pixels in a surface. And we should bracket that with lock and unlock. Okay. So I guess we'll have to update the pixel data through the C pointer. I guess so, because you can get a pointer to it, but then from there it seems like the API is like, meh, it's up to you, sir. Yeah. Okay. So somehow we're gonna have to set the pixels through that pointer somehow. So let's get it first. Let's construct it one step at a time here. Baby steps. Right, baby steps. Okay. WC texture. Okay, bring that into scope. Okay. So output is going to be create RGB surface. Full of arguments, few arguments probably. Recall. Do a V2 size and a pixel format. Alright, so we got the V2 size can come from the WC texture, I believe. We have that in the structure, if I'm not mistaken. It's a new type, texture, which is an array, which has the bounds, which we can get the size from. Okay, that's going to be a word. So we get the width and height. I'll say T width and T height just in case, and that'll be something on WC texture, get texture. That'll be array.bounds. Okay, and now that we have width and height and scope, if everything compiles properly, we will probably need to map that. To integral. Or choose the operator. And then just one more hole, our pixel format. Which I think image. Right, image load. Okay, maybe we don't know. Well, we kind of know. So I think we were looking at it before. I'm just guessing at the moment from what I remember, but I believe since our input, in our particular case, our demo image input is a PNG file, it should be RGB 8888. RGBA 88888. My editor's giving up on me again. Oh, array is not part of my world here in the main application. Right, so we're going to open package. Add that as a dependency to our executable. Oh, come on. All right. And then we can import data.array. Unless I have a function, I do. No, it just gives me the size, which should be the same for width and height. Or no, well, no, it won't be. This is assuming a square texture, which is true for the patterns, not true for the output grid. Necessarily. Okay. So we got the there's our output. Word. Okay, so TW is the lower bounds. Okay, what is an SDL wants v2 of int. Let me look up the SDL documentation of that. That's the one. So once it has the width and the height. So the max of those. Okay. So in our bounds function, we actually... This isn't width and height, this is like min and max. We don't care about the first element. This is going to be the th and the t width and the t height. Okay. This is giving, like, doing this right now is giving me a lot of, like, information about, like, how much code we still need to wrap up to make this usable, because, like, the user of this library shouldn't need to know that, like, the texture is implemented as an array and in order to get the bounds and the size of the thing and whatnot, in order to create their surface. So definitely have to fix that up. SDL dimensions, surface dimensions, that's fine. Like, we should be able to handle that. And then, of course, all of this code here that constructs and sets everything up needs to be wrapped up as well. So it's kind of a good thing to, like, dog produce stuff and, like, figure out where the bounds should be. You want to get better at API design. In Haskell, it's kind of not determined for you. Like, there is a bit of an art to it. But the types really guide you strongly in the design. Okay, so we got the width and height. Let us now get our RGB surface. So technically we should have that in output and scope as well, a surface. Okay. And so that's allocated. And that must, I guess that must be retained by the library. Technically it's a pointer. Okay, null of the fill calls. Yeah, that's right. So on the Haskell side of things, we get the surface structure back, but really that's allocated by SDL. Okay. Okay, so that's why we gotta lock and unlock things, I guess. And if it's in this M, we could get a runtime exception when we go to construct it. Okay, so that totally makes sense, that's fine. Okay, and then we're going to need bracket for getting the surface pixels out. in order to change the state of this surface before we return it. Okay, cool. Bracket. That comes from control.exception. Alright, so that's the release resource function. That's the one we're going to run in between. That's the acquire resource function there. Alright. And let's see, lock surface is our M. And then unlock surface is also same, so that should all line up just nicely. So let me go, oh, we already got control exception scope, awesome. Okay, so then bracket, lock surface, let's output, unlock surface, and also output. And then our function is last. So we got the surf. Right. Boom, boom, boom. Oh, that surface is unit. Okay, so L surface doesn't actually do anything here because our acquiring function returns unit there, so the type of our input function here is going to be unit. So we can just ignore it. And just use output, I guess. Oh no, you gotta use the function to actually get the pointer to the pixels, and then we can manipulate those through the pointer, right? Yeah, this function, surface pixels. Pixels. Surface pixels of output. Okay, there's our pointer. Okay. So now how do we manipulate that? That's the last step. All we got to do is iterate over our texture array, setting the pixel value we have in there into this output surface. And then Bob's your uncle, I guess. Oh no, we gotta, after that, we've got to then return the surface, I guess. Yeah, so that's all we have to do in that step there. Okay, so manipulating pixel data through the pointer from Haskell. I believe that is through the whatchamacallit type class. Oh, bother, it's not coming to me. Storable. Possibly the Marshall. Okay, this writing values of primitive types to raw memory. Yeah, storable. Okay. Alright, so we can poke a value there to write it to that given memory location. So we give it the pointer. Ooh, Currently, our pointer is a pointer unit. So we're going to have to do some casting again here to convert that over to the CU int that we need. Yeah. So that this storable poke is not pointer unit, which is like a void pointer. Because the A's we want to be the pixel type. Just CU ints. So we're going to have to do this cast business again. So look at this void pixel pointer. And then we'll cast that using the same kind of trick. And then we should have that in scope now. Add pointer CU int. Okay, so as long as our cast is proper and right, we won't offend the segfault gods. As long as we stay within the bounds of the region of memory we've allocated here for this surface. Okay. So I think we're going to have like a similar bit here. Only we don't need to keep the return value here. We just need it for the effect. So there's a version of sequence for that. Sequence underscore. We're going to set the pixel from pixel pointer at x and value y. Right. So x and y, where are x and y going to come from? They're going to be from the association list from the array of the doohickey. Blah, blah, blah. You know, the blah, 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 the WC texture. The array of that, though. See texture. Get texture. Not really expecting this to compile just yet, but yeah, because we haven't defined set pixel. To integer from integral. That's the one I meant. From integral. Okay. That's going to type CU int. cint index and cint value. It's going to be just IO units. Okay, so then that's going to be through storable, the poke. Oh, we got to poke at an offset. There we go. Poke byte offset. So, C, the way C structures arrays, right? An address in memory plus some offset. Based on the size of the elements. Alright, so... oh, it can just be plain int. Doesn't need to be cint. Okay, and then our A. Okay, so that should all just fit in there. And then it's IO units return type, so... poke byte offset, or poke byte off. In fact, I think all the arguments are just in the right order, so it's literally just that. Okay, almost. And 49, there we go. Output wave state. Did I? Yeah, mistype thing. Okay, almost. Right, okay, so each X is actually a tuple of word. Right. Right, so SDL surface array is going to be flat, the indices in it. So we got to convert our index, our two-dimensional index into that index, into the SDL's array index, and so we can compute the offset. There, that should be pretty straightforward, hopefully. Okay, so as long, well, we're doing depending on how the arrays are structured in our output, this is going to matter for anybody implementing this stuff too, but the order in which you store the elements of the array at the indices, right? So if we're like doing a square, but we only have like an array that just goes from 0 to 100, but there's like 10 by 10, a 10 by 10 square. We can sort it column-wise, perhaps, or we can go row-wise. I think the texture, that's just usually what I use. I think the texture type is all row-wise, row-oriented. So the formula for converting row-oriented indices into our flat indices, so from like 1 and 2 into wherever that should be in the 0 to 100 or 0 to 99 array, would be the width of each row times the current row we're on plus our offset into it. width. So I'm going to put a hole there for a minute because this is really... and I'm going to change y to be the value v. So that this is really that. Alright, so in order to get where we are in surface array, our offset into it, we need to take the current, we need to multiply y by the width of each row, and then add x into that, and that should be our pointer off, our offset into the surface array there. So that would be y times texture width plus x. And because the number conversions... I'm just gonna do it like this. Couple of things, okay. Okay, so sorry, we got a couple of errors with our, let's see, our use of bracket here. And, okay, maybe the problem could be with unlock surface there. Maybe not enough arguments. And then some conversion error issues with that. Okay. That's gonna be kind of annoying. To like convert it from integral on every step of this iteration, which I don't exactly want to do. Okay. That's gross. I don't like that, but it'll be fine for now. Just to see that it works, and then we can clean this up a little bit, hopefully. Okay, so then we just have to deal with this unlock surface stuff. Okay. Bracket. Okay. Expecting to return an IO of C. Okay, right now we're returning IO surfaces, so he thinks bracket underscore, and perhaps ignoring some results. Okay. Oh, okay. There we go. Then we don't get the argument. Okay. Compiles. Does it work? Let's see. Did we offend the gods of doohickiness? We haven't locked up. Oh, yes, we have. Yeah, the application's not accepting input. Something's happening there. Hopefully that actually died and killed it. Okay. So it's kind of there, but I'm just seeing flat gray. It looks to me like it's not quite doing what we need it to do here. I'm wondering if it's like just a data thing with the surface stuff here. Like maybe we got the wrong pixel format. Maybe this expression's... I don't think it's gonna run forever. We know the output text. Maybe it's just taking a really long time to generate. That could be a thing. Okay, we haven't... I'm gonna let it kind of hang out for a little bit and see if it's just our attempts at the output image are just too big for our dumb algorithm. And, just give it a shot. Maybe we should try it on some smaller input. Or try to generate a smaller output image. So I expect if it's trying to do accesses out of bounds as we're trying to like manipulate the pixel data on the surface, that would segfault, hopefully. Right. So, but we're not, it look like maybe we're not even getting to that part. Okay, I'm gonna try. Let's make sure. Maybe it's a data size problem, and like our implementation is just that terrible in performance. Possible. Very, very possible. Yeah, let's make our output texture size 15 by 15. Maybe not. Okay. There. we know this function works. And we get from surface. X goes from 0 to image width times image height minus 1. It could still be our set pixel stuff going off, because I'm not sure if this bounds is properly in the array bounds. Is a proper offset. That's a possibility there. Because this is our input texture data, so it gets past there. Okay, so that means we can try rehydrating. Okay, before we case match. Maybe the algorithm is just taking super long. Okay, no, it's getting there pretty quick. Yeah, so it's not an algorithm output problem. Probably then the pixel accessing stuff that we're doing in setPixel maybe. So maybe we're not setting quite the right offset here for X and Y. We gotta just offset it by 1 on the width there. Let's print the output WFC texture. Cool. Oh, interesting. Okay. Okay, so right, kind of makes sense. I think it is probably the algorithm actually. Perhaps. Okay, so you see me poking around here, printing out stuff, right? So like Haskell is a lazy language, right? That's what it is. So when I put the action here to put streetling hello, for example, right? Of course it's going to print. Of course it is. And the reason why is because we haven't nothing has forced output wave state to actually evaluate anything yet, because we haven't used it. So, right, so Haskell's not even going to compute it if we don't use it. So if we put this here, it's like, okay, yeah, we got past here, but we haven't done anything yet. So it's only when we evaluate the output wave state. Basically, when this function comes in here and demands some values out of it, when we go into make output texture, that's where it's going to start doing things. And running. Right. So I print that here, but we're not getting to that print. We're not getting that print statement. And if we go in the library, we go in to make texture, output texture here. Right. And I put. I have to use debug. Import debug.trace as debug. Will we even see this debug.trace message here? I don't think so. Oh, we're in one out here. Hello, Elemental Magic's card game. What's going on? I'll do it as a trace M here. Can I implement this algorithm using a bazaar? I don't know what that is. Would you care to elaborate, Elemental? Alright, so we get to that hello because we still haven't evaluated anything yet, right? Oh, from EdConnect's Lens Library. You know, I don't know. Let me take a look. Bazaar, okay. Yeah, maybe, you know. So what is a bazaar? It's used to characterize a traversal, aka also known as the indexed Cartesian store comonad, indexed clean store comonad, or an indexed fun list. Commit libraries, jeez. Super great. A bazaar is like a traversal that has already been applied to some structure. Where context, I think, holds a and a function from B to T, bazaar ABT holds n A's and a function from n B's to T, where n might be infinite. Mnemonically, a bazaar holds many stores and you can easily add more. This is a final encoding of bazaar. It's bizarre. But yeah, no, I haven't used this. Haven't used it at all. I'm sure once you use it and learn it and you sit down, you're like, okay, I'm gonna figure this out. You will totally get it and it'll be amazing. And maybe it'll make your code just a little bit more succinct. sometimes it just it takes like there's a battle to get there, you know? Real battle sometimes to get there. And I had there's this interesting conversation actually I had recently. Yeah, bizarre is actually a definition in it. That's hilarious. Um, but I had this kind of discussion on Mastodon on Mastodon recently on the Fediverse. You've used FunList before. Oh, okay, cool. Honestly, my lens foo doesn't go a whole much further than like view and set. It's pretty much it. Yeah, it doesn't go much further than that really. I've figured out how to use those and I use them and that's good. Anything more advanced than that I haven't really. So yeah. Anyways, the conversation I had on the Fediverse is basically about how in functional programming and languages like Haskell, right, you can go on, it's in my notifications somewhere. Yeah. Basically, somebody was talking about dependent types and how like they're so used to it and it's like just a nice way to program stuff. And I totally believe them. Like they said they learned Haskell or Agda first. Yeah, Raymond said using Haskell as my main language at work is pretty great, except for one thing. Having learned Agda first, if you don't know Agda, it's like a dependently typed functional programming language. Probably originally used mainly for theorem proving, but like I guess could also be a full-on programming language. Anyways, it got really used to having dependent types at my disposal. Now I often find myself naturally thinking of a solution that makes use of dependent types than having to translate this solution into Haskell. Because Agda, I guess semantically and programming language wise has just more going on at the type level. More interesting things going on there. Whereas Haskell people say is like simply typed. Agda's dependently typed. And so there's just more power there, I will say, to keep things kind of simple, glossing over a lot of stuff and details. And so like going from like a superset into a subset language, right? Because Haskell kind of has dependent types, but not really. So how you encode things is going to be pretty complicated in Haskell than it would be in Agda. So, of course, there's always a translation. But the translation may obfuscate what the code is doing, making it harder for future programs to understand it and maintain it. Because you have to encode things into the subset language. Elemental, you've seen some Agda too, but I haven't coded in it. You've done a lot of interest though. Cool. Yeah. I think the overlap of people who've done Agda and Idris, like there is quite a bit there, but they're fairly distinct still. Yeah. And I've had this problem as well, but I think most programming can be done without dependent types. Also, lightweight dependent typing is doable in Haskell. Yeah. Yeah, I've done a little bit of lightweight dependent typing in Haskell myself, for sure. Even at work. But, as we'll get into in the thread here, I try to keep it very, very small and very, very contained. For reasons. So, but the translation may obfuscate what its code is doing, make it harder for future programs to understand and maintain it. The work I do is no relation to formal verification, nor is it mission critical that the code is correct, but I still find myself wishing I could use dependent types, just because they make writing programs and capturing business logic both faster and easier. A language with dependent types requires a less severe translation from the programmer's ideas to a compiling program. Okay. And that's what Elemental's pointing out as well, and been my experience as well, and something I kind of replied to in this toot. Well, I kind of hint at it more in my reply to the toot, where basically like dependent types in Haskell are encoded so weirdly it's getting better because a lot of people are putting effort into this, but they are encoded a little weirdly. That it can be very, very off-putting for people who are kind of newish to Haskell and don't understand these, like how the dependent types are encoded in Haskell, and like they just have so much more to learn in order to use that code, right? Right, so I say that's interesting. I use Haskell full-time as well. Although I've used dependent Haskell a bit, I feel as though I need to keep its use under wraps and hidden behind a module API. Right? Because like when people join your team and they're just learning Haskell, like just learning the simply typed lambda calculus and just like Haskell's version of it and trying to figure out all the things that are going on in this language is hard enough, right? Hard enough that when developers, and like I do Haskell full-time at work, and we have a very large Haskell code base at this point. It's well over 1 million lines of code now. When we end up using more advanced type level things, it gets really quickly difficult for new contributors to ramp up and onboard into the project and get started and get running, right? And that's constant, that kind of like value of how much power do we want to leverage out of the type system versus how easy do we want to make it for people to understand and onboard newbies to the language and to our backend is the thing that we're constantly tweaking, because we tend to hire, because the Haskell community is quite small, we tend to hire people, I would say the majority of people from outside of the Haskell community now, and people who are maybe programming in Haskell for the first time, right? They may be very senior programmers, but they're senior programmers in C# or senior programmers in Java, senior programmers in whatever, and they're coming to Haskell for the first time and learning some of these concepts at first. So for them, seeing the weirdly encoded dependent types is like, meh, no bueno. And if I was going to, and this is the roundabout way of me saying like, even the use of lens is heavily kind of like tweaked, I would say, in these kinds of discussions, like how far into the lens library can we go? We do have some uses out of it because it is just that awesome. But things like Bazaar, I'm low on to learn because I'm interested, because it might actually make this algorithm easier to represent for a lot of these indexing sort of operations that we have to do on it, but it's something to think about, you know? Yeah, and Elemental is saying, yeah, one of the big benefits of types is helping with refactoring, but using dependent types often does the reverse of that, requiring you to rewrite all of your proofs when you change the structure of things in a trivial way. Yeah. Yeah, a friend of mine does a lot more work than I do in dependent types, and like he works in it full-time doing proof engineering, essentially. And that's been his advice to me over the years, is like, don't get carried away with dependent types, basically. If you try to write everything and specify everything to the nth degree in them, you can code yourself into a corner where trivial changes break everything. The Lens library inspired you to study more category theory. Yeah. I've been focusing on leveling up my non-dependent type programming and finding there's still a huge amount of type theory to learn. Yeah, there is a lot of type theory to learn, and that's like this. The skill ceiling in Haskell is really, really high, right? It just keeps going. There's, even without dependent types, there's still a lot to go on. There's like a lot of abstract algebra you could learn that is so useful in Haskell and doesn't require the use of dependent types. A lot of category theory is still applicable. I think type theory gives you a way to organize all of these things into a way that a computer can understand, and kind of like formalize what you're thinking. I feel like lenses are not that useful with overloaded record dot pick. Yeah. Folds and traversals are complicated for a newcomer. Yeah, that's kind of been my experience. I still think even with overloaded record dot, lenses are useful because of set and like over and stuff. Is still really, really useful for updating deeply nested structure in a kind of uniform way. And I've seen some libraries in the Haskell ecosystem, and we've built some stuff with them on this stream, that use lenses in order to provide generic setters and getters for library-provided data structures, which can be super useful. For example, graphics libraries like Monomer is like I guess it's sort of like the functional version of an intermediate mode API style graphics API, but in order to update widgets and stuff like that, they give you a lot of they expose setters, lenses for you to use, and for the library to use to get into your data structures that you pass in and define. So I think lens is still very, very useful in a lot of contexts, but overloaded record dot, you see me using it on stream quite a bit in this code base, definitely does lower the amount of lenses you would maybe use in a Haskell project from like 5 or 6 years ago. Yeah, exactly. So like passing lenses around which hold on to, yeah, exactly. So still quite good stuff. Yeah, I do appreciate them, like them, but you can go really bananas with them. And like the Cometaverse is filled with cool, fun stuff with like that, but it's quite the thing. So you gotta be careful. You gotta pick and choose where you use that stuff for sure. If you're coding your own stuff, go hog wild and tell me about it and write about it, and send me a toot or a blog post or something. Yeah. Yeah, it's pretty interesting. Like, Komet seems like one of those people who's really kind of internalized type-driven development to an nth degree. Like, really understands it at a fundamental level. Nice. Yeah. In this code, which is on GitHub, and I'll give the link to that later, it's very, very basic. I mean, I do some traversals and stuff, obviously, and sequence and things like that here and there, but I don't consider that terribly advanced at this point. Yeah, okay, so our current problem here with this code is that it's getting basically hung up at some point. Maybe it's the algorithm itself. Maybe it's just the implementation is super slow. Maybe we're outside of our small little test case here, our real world use is like messing things up in terms of like how it's evaluated. Like maybe the data structures are just big enough that we're getting some kind of leak somewhere or something. Yeah, so output texture. Right, we're getting the trace m hello here. Will we still get it here when we go to traverse the wave state here and get the grid out? All right. Good old lazy evaluation. All right, now that we're forcing that value, so now it's like computing everything and running everything. So yeah, it probably is looking, very much like it's just going super, 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 super slow. Maybe it's making progress. I wonder if it's getting where it's getting hung up and how we could find that out. Oh, there we go. Okay. Okay, so it is pretty slow. I'm just getting blue pixels though, so that's no bueno. Okay, so I think the performance problems are going to be pretty obvious once I start looking at this. I'm using lists somewhere that I shouldn't be, and I know there's a couple places where they shouldn't be used. However, even if it was slow, it should be right, and this does not look right. So there's something off with this. Okay, first off, this is the texture data printed out from our output texture. All 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so we're probably maybe not preserving the pixel data properly. That would be my guess. Yeah. That's probably what it is. Okay, so that is all implemented in main, but I think we're out of time for the stream this week in order to handle that. So I'm going to commit what we have so far. And next week, we're going to clean this code up a little bit. We're going to wrap up all of the code that we've talked about on the stream that we need to wrap up, which we can probably review in this where did it go? In all of this. Right, this stuff here. Right, so we added... This is all internal functions that we should probably like cover up so that the person, me, using the WFC algorithm here, only has to provide implementations for, converting from my texture format into the WFC, not even, maybe, yeah, even provided that function to me. I want to be able to write this in one function. And so as long as you give the library that function for converting to and from your texture format, we'll handle all of the internals, like setting up the pattern results and creating the initial wave save and running the algorithm and all that stuff. So that you, as an output, just get case match of the results. Was there an error? Was there not? That kind of thing. And make that API nice there. So we'll do that next week. And then we'll have to look at our get pixel and set pixel implementations here to make sure that we're preserving the pixel data according to the pixel format of the SDL texture all the way through, because the algorithm itself doesn't mess with the pixel data at this point. So unless we really, 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 really messed up something inside wave function collapse in the algorithm itself, it shouldn't be able to do that. So I think that's probably what's going on there. So this is an us issue, a skill issue here that we're going to fix next week. So let's get to that commit. See, here we go. Add wave function collapse to visualizer. It's probably very descriptive. Convert the SDL texture. Set everything up. Run the algorithm. Convert back to SDL Surface. And render the results. But it's still not working right. Probably messed up. Like pixel data. Okay, pushing that up to main. All the code for this project that you have been hanging out with me and watching and following along with is up here on GitHub. I'm Agent Ultra. I'm Agent Ultra on GitHub. I'm Agent Ultra on Twitch, on the Fediverse as well. So you can follow me at the types.pl server. I'm Agent Ultra there. You can follow me on the Fediverse if you're on Mastodon or whatever. I usually post updates about the stream and things that I'm working on there, so you'll get updates on that. You could also just write this down. I do streams on Tuesday evenings about 10 after 8 in the Eastern time zone. And if you are on Twitch and you like subscribing to channels like mine, and you have your notifications set up, subscribe, follow, and you'll get notified when I go online and do these streams. And you pop in that way, because sometimes I do streams at other random times every once in a while. So yeah, and if, of course, I back up all my VODs on YouTube. There's a link to that in my profile on my Mastodon server there. So if you're watching from there, give us a like, subscribe, all that stuff, and you'll get notified when I post new videos and VODs. It's been a pleasure. May all your monads be free and your types always check. And hopefully I will see you next week. Take care out there. Happy hacking. See you soon.